All right, welcome back. One more concept I forgot to mention before I get into path independence, and that's a concept of called simply connected. Not quite the same as connected, it's connected but with no holes in it. So for example, if I wanted to draw a couple pictures, here I'm going to draw a picture of something that's connected but not simply connected. Okay, you got a little donut here. Okay, I still could connect any 2 points, but it's not completely connected because we've got this hole in the middle. I know, right? All these sort of things. Oh. Okay, now we're ready for path independence. Okay, path independence. Let's just say what it means. All right, let me write it in by hand. If F is a continuous vector field, okay, let me write it. Maybe I'm overkilling by writing so small. Okay, so if F is a continuous vector field, okay, with domain D, okay, where we consider domain right now to be an open and connected region, then the integral over a curve of F dotted with dr is independent of path. Okay, or path independent. Okay, if the integral over one curve equals the integral over another curve where C1 and C2 have the same endpoints. Okay, so all we're doing here is we're just defining what it means. What the heck happened there? Press something I didn't want. Okay. All we're doing here is we're defining what it means for a line integral, a vector line integral, to be path independent. Is that, I can go over this curve or I can go over this curve, and it's not going to make a difference. Okay, as long as I have the same endpoints. Okay. And now we're going to have the theorem. Well, not the first theorem, but one of them. First theorem, which is actually pretty clear, and so I'm not even going to bother proving it, but I will state it. Okay. The line integral of F dotted with dr is independent of path in D. if and only if the integral over gamma of f dotted with dr equals 0 for every what we call closed path in D. Okay, and all a closed path means is that it has the same end, the end point and the initial point are the same. Okay, so I'm not going to really prove it, but I'll just show you a little illustration. Okay, let's say we have some gamma, which is a closed path. Okay, all I have to do is then I just pick a point here, let's call it R1, pick a point here, call it R2, and let's go around this way. All right, so let's split it up now. We have this path. Let's pretend it looks like the other one, the bottom of the other one. So we're going to call that C1. No, let's not put it there. And then the other one we're going to call C2. Let me put that in a different color. Now, I want you to notice something. Here, this arrow is in the opposite direction. Okay? And why? Because the integral over gamma, the integral over gamma is going to equal the integral over C1. Why did I do that? The integral over gamma is going to equal the integral over C1 minus the integral over C2. Okay, now I'm going to write it. The integral over gamma of f dotted with dr is going to equal the integral over C1 of f dotted with dr minus the integral over C2 of f dotted with dr. Okay, so here you have the minus integral over C2, whereas here it's the positive. So now, if this equals 0, then these two things are going to be the same, right? That's all there is to it. Okay, so it's not really a proof, but if you saw a proof, that's what it would look like. Okay, all right, I'll see you guys in the next video.